Pictured here are two molecules, water, H2O, and methane, CH4. If we draw the Lewis structures of these molecules, we can see that each of them has a steric number of 4. There are 4 places where I am arranging electrons around the central atom. So if they both have a steric number of 4, then we would expect them to have the same shape. But they clearly don't have the same shape. That's because the steric number tells us about the electron arrangement around the central atom, but the shape of the molecule has to do with the arrangement of the atoms around that central atom. And that's because we cannot see lone pairs. We can only see the atoms that are around the central atom. And so if we want to know about the shape, we have to connect the electron arrangement to the arrangement of atoms around that central atom. If we want to predict the shape of a molecule, we have to be able to go from the electron arrangement to the atom arrangement, just looking at where the atoms are. So we start by thinking about our steric number and thinking about how those electrons are arranged, because that's going to dictate where we put our atoms. So both of these have a steric number of 4, water and methane, both have a steric number of 4, and so their electrons are arranged in a tetrahedron. So I start by thinking about those electron arrangements, and then I'm going to actually get rid of my lone pairs. Because I can't see the lone pairs, it's as though they aren't there. And so if they're not there, I can't see them, and they don't contribute to the shape of the molecule. So if I'm looking at water, and I remove where those lone pairs are, keeping the atoms exactly where they were when those lone pairs were there, I end up with the shape of the water molecule, which is bent. So I can see that the oxygen has the hydrogens at approximately the tetrahedral angle of 109 degrees, and so it is bent. On the other hand, if I look at methane, there are no lone pairs, and so I don't remove anything, and so the shape that I get from the electron arrangement is the shape of that molecule, because each of the electrons that are arranged around that central atom are terminated by an atom, and so I know where they are. And so if my steric number is equal to my number of atoms, then I just have the same shape as the electron arrangement. I can organize this information into a table like the one shown here. So across the top row, I have the steric number. This will dictate the electron arrangement. And then down this first column, I have the number of atoms around the central atom. So we can see that if we have the same steric number, 2, as the number of atoms, 2, then we get the electron arrangement and the shape are the same. So steric number of 2 is linear, and if both of those places where I'm putting electrons are terminated in atoms, then the shape of the molecule will be linear. So for a steric number of 3 and 3 atoms, I have trigonal planar, which is the shape of a steric number of 3. 4 and 4 is tetrahedral, 5 and 5 is trigonal bipyramid, and 6 and 6 is octahedral. So if I go down the diagonal of this table where the steric number and the number of atoms are the same, then I get my basic electron arrangement shapes that we talked about in the earlier video. To get the other shapes in this table, I'm going to start with my electron arrangement, just like we did for a steric number of 4, and I'm going to progressively remove an atom and replace it with a lone pair. So if I have a steric number 4 and 3 atoms, then one of those steric numbers is a lone pair. And so if I do that, I get a trigonal pyramid. So let's see how that works. I would start with my central atom, and then I would have, I would know that my arrangement of electrons is going to be a tetrahedron. And so I would have an atom at the end of 3 of these, here, here, and here. But the last place where I'm putting electrons is a lone pair, and so I would want to not worry about this lone pair, remove that from consideration, and what I end up with is this pyramid shape that has a triangular base. So all the sides of that pyramid are triangles, and so that's a trigonal pyramid. Now if I remove one more atom from that, so if I have 2 places where I have lone pairs and only 2 atoms, then I'm back to my water molecule, which we know is bent. If I do the same thing for each of these steric numbers, so if I start with my trigonal planar steric number of 3, so I know that my atoms are arranged in the plane of the board in a triangle, and now I simply remove one of those atoms and make it into a lone pair, then I only have 2 atoms connected. And so I have to remove this lone pair to get the shape, and it is bent. So if I start with my trigonal pyramid, I'm going to draw it down here because it's a little bit trickier to draw. It's a little bit bigger. I have my pole atoms, and I have my atoms at the equator. There's my 5 atoms around the central atom. If I remove one, I am going to get the next shape, right? Because if I replace one of my atoms with a lone pair, then I will be left with 4 atoms and a steric number of 5. So here's the tricky thing about steric number of 5. Remember that in the steric number of 5, there are 2 different angles. I have the angle between the poles and the equator, which is 90 degrees. And I have these 120 degree angles between the atoms that are, or the electrons that are on the equator. And the deal here is that lone pairs take up more space than bonding electrons. Bonding electrons are kind of contained to be in between the 2 atoms, whereas lone pairs can kind of spread out. And so if I want my lone pair to have as much space as possible, then I want to give it as many 120 degree angles as I possibly can. And so I'm going to remove atoms from my equator first in order to get these other shapes. So if I remove an atom from the equator and redraw that, so I have an atom up here and an atom down here, but I've removed the equator atom, so I just have one here and one going back into the board there. This is what's called a seesaw shape. If I take this shape and I rotate it, let's see if I can do that. So we'll just rotate it around. Then if we look at this, it's kind of like a teeter-totter or a seesaw. So I have one seat here. I have my bar that goes between that and the other seat, and then I have my little fulcrum that's holding that, and then I can seesaw this up and down, and that's a seesaw. So we call that shape a seesaw just because of what it looks like. So if I continue to remove atoms from the equator, so I remove another atom from the equator, then if I remove, let's say, these 2 atoms and leave this equator atom and these pole atoms, then I will have 3 atoms with my steric number of 5. And so if I do that, I'm going to end up with a shape that looks like a T. So that is called a T-shape. And then if I remove the last equator atom, I will end up with my linear shape. So going from all 5 atoms, remove one, make it a lone pair, I get the seesaw shape. If I remove one more of these equatorial atoms, remove 2 and leave one of the equatorial atoms, I'll get this T-shape. And if I remove all of these equatorial atoms, I end up with this linear shape. So we can do the same thing for the octahedral shape. And if we do that, remember that the octahedron starts out looking like this, with these atoms around the middle, 4 atoms around the middle and an atom top and bottom. And here, the first atom I remove doesn't matter because all the angles are 90 degrees. And so I can just remove any one of these atoms and I'll get the same shape. So let's imagine removing this bottom atom down here. And if I remove that, I'm going to end up with a shape that looks like a pyramid, right? There's 4 triangular faces, but the base of that pyramid is a square. And so I call it a square pyramid. Now, when I remove the next atom, I'm going to have to be careful because I want to make sure that I'm removing it in such a way that I give my lone pairs as much space as possible. Remember that there is a lone pair down here. And so I'm going to try to put my next lone pair as far away as I possibly can from this lone pair that's already there. And so if I put it up here, it'll be 180 degrees away, and that's going to be the best possible situation. So I'm going to remove this next atom from here. And now if you imagine this shape, where we now have our 2 lone pairs that are 180 degrees away from each other, as far away as they can possibly get, then here I just have a square. And if I tip this square up, so if I just sort of tip it up into the plane of the paper, I can see that I actually have a molecule that just has a square planar shape where I can put all of those atoms in the same plane and they form a square. So that's called square planar. Now when I remove another atom away and make another lone pair, it won't matter where I take it because they're all, again, 90-degree angles. And so I can take it from anywhere. And no matter where I take that atom from, I'm going to end up with atoms that are in a T-shape. So I just removed an atom from over here and made that a lone pair, removed this one, and then I just redrew it so I can see that it's a T-shape. And when I remove the next atom, now I have to be careful again, because again, I want to get all the lone pairs away from each other as far as possible. And so since I have a lone pair over here, I'm going to put my other lone pair over here so that these 2 lone pairs don't have to be next to each other. I'm going to put it over here so it's 180 degrees away from that lone pair. And if I do that, then I end up again with my linear shape of a molecule. And so you can see how we can just build each of these shapes by removing an atom and replacing it with a lone pair.